tutorial 6, everybody. And we'll talk about, very briefly, logarithmic differentiation. Okay, so this is helpful when you've got something messy and complicated and ugly and involves products, powers, or quotients, and this can make your life bearable in some cases. So, what do? I'll just do an example. Okay, we'll prove the power rule general n. I'll say non-zero. Yes, I'll say non-zero. Non-zero. N. Okay, I showed that it was reasonable for, what is the power rule? For those who've forgotten. I mean this thing. And the perennial reminder, don't confuse power functions with exponential functions. Amongst other things, they have very different derivatives. Okay, so I showed you from first principles how this happens for n equals 3. And I think we also did it for n equals 1/2, so the square root function. And I said, using other methods, we can prove that it works for all n. So let's do one of those other methods. All right. So, first I say let y equal x to the n. Then I take logs of both sides. Okay, step 1 is write something like this. Step 2 is take logs of both sides. Step 3 is use log rules to simplify or modify in some way. So here we'd have ln y equal to n ln x. Volume's okay? Including, you can hear me, right? Oh man, the back? Yes? Okay, that's cool. All right, good. Okay, let y equal the function of interest, take logs of both sides, fiddle around using log rules, and then differentiate. So look, more implicit stuff happening here. Okay. All right. What is the derivative? Okay, so this n is a constant, so it pops out. The derivative of ln x with respect to x is just 1 over x. So that's good. The derivative of ln y with respect to y is 1 over y. Okay, but we want the derivative with respect to x, so that acts as an inside function, so we multiply it by the derivative of y. Okay? Differentiate with respect to y, and then multiply by the derivative with respect to x by chain rule. And over here, all we did is know the derivative of ln x. Okay. So, write logs, rearrange, take derivatives, use chain rule, and whatever else you need, and now you solve for the derivative, like we always do. N y over x. Okay, and like we've seen before, we want something in terms of x. So, in this kind of situation. So, y is x to the n. Plug that in here. Da, 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 da.
We can't see.
Oh, come on. You ruined my climax. Where are we? You can't see this.
Yes, well,
the screen.
thanks.
How many screens are in your way? This one?
No, the big one.
Oh, yeah? Yeah.
So you should be able to hold it down.
Yes.
No.
Was that no as in I'm doing it wrong, or no as in it's not
just
possible?
any word.
I said
No,
double.
it'll be fine. Then the
I reckon you'll survive. So, yeah, if you can't see stuff, tell me, but, ta-da! Okay? Differentiate, use chain rule if necessary, solve for the derivative, sub in y equals x to the n from over there, and then laws of exponents. Okay? And ta-da, we got that amazing thing. And we didn't have to do anything from first principles, and life's good. Okay. Now, let's say I'm nervous about something and I can't remember what I'm nervous about. Oh yeah. Okay, what's the problem here? What can't I take a log of? Something that's 0 or less, yeah? So this only actually worked. All of this only really worked for, can you see this?
No.
Can you see this?
Yes.
Yes.
That's interesting. It's like a optician. Optometrist?
Okay, thanks.
Okay. Okay, log can't take non-positive arguments, okay? So none of this is kosher unless we have this, okay? So we've really only proved it for that. Okay? So there's something we could do, and again, this is so optional that I'm nervous now. But we talked about how the derivative of ln x is 1 over x, and we said how that's valid only for positive x. But the derivative of ln minus x, okay, ln minus x has domain x negative, and it's differentiable there. So how do we get this derivative? We use chain rule. Okay, we go 1 over minus x times the derivative of minus x, which is minus 1. So minus 1 over minus x. Hey, look, it's 1 over x again. Okay, so that was the missing piece. Yeah? So, ln x has that derivative, ln minus x has that derivative. So, can you see this? So ln absolute value of x, okay, which is equal to ln x when x is positive, and ln minus x when x is negative. So this guy has derivative 1 over x, pure and simple. Very bad for space here. Again, we'll get out of this in a moment. There we go, that's it. Okay? So you find the derivative of ln x, it's this guy. Derivative of ln minus x is that guy. And ln absolute value of x is that. And so the derivative of that is 1 over x everywhere, except 0. So there. Good? Okay, so if we know that, I deleted something, haven't I? So, this guy works for x not equal to 0. And my problem was that this only worked when the argument was greater than 0. But if I edit this, and I put absolute values around everybody, okay, this now works for x to the n not equal to 0. You get the same derivative, and everything else works out the same. So there you go. So now we proved it for x not equal to 0. Okay? And if you want to prove that x equal to 0, you go by first principles. Okay? So use the definition of the derivative. And there's your proof. I believe everything was optional. Okay? Questions? All right. Nifty tool that turns up from time to time. Okay, and this logarithmic differentiation thing is also good. Logarithmic differentiation is also good when you want the derivative of some function of x raised to some other function of x. Okay, so for instance, if someone asks you to differentiate x to the x, you do this kind of thing. You take logs, apply the log rules, differentiate, and then solve. Okay? Okay, I'm going to stare at it. Okay, any questions? Okay, if that's confusing, you either ask me or you forget it. Okay, I'm going to briefly go over the logistic growth model again, because I'm not sure how much sense it made. And again, this isn't vital for any important reason, it's just that it's an example and you might as well understand how each piece works, and many of you are biologists, and so this may be important to you. Sorry again, people. And of course it's yellow. Okay, we've seen this, yeah? So I put 3 versions of the thing up here. So what do we got here? Over here we got the relative growth rate. Down here we've got the growth rate. Okay, relative growth rate is like per capita growth rate. Okay, so what's the rate of change in the population per person? This is just what's the rate of change in the population. And those are the trajectories. Okay, so if I start here, the population does that, which is your usual picture of a logistic curve. Okay, so I'm going to go over the pieces of this, and then I'm not going to mention it. Okay, let's look at all the pieces. What goes on if the population is 0? Okay, the population is 0. That guy doesn't make sense because you'd be dividing by 0, so forget that. Over here, if population is 0, that's 0. Okay, you put a 0 there, put a 0 there. This will obviously be equal to 0. Okay, so the growth rate is 0. When the growth rate is 0, you don't go anywhere. So if you start at 0, you stay at 0. So that's that piece, which is boring. Okay? Slightly more interesting. If the population is small, okay, so if the population size is much less than the carrying capacity. Okay? I should probably say what these axes are. Okay? That axis is sort of like time. That axis and those axes are the population as a fraction of the carrying capacity. Okay, so when the population is much less than the carrying capacity, the relative growth rate is almost k, okay? Because if p is much less than m, then p over m is much less than 1. 1 minus something much less than 1, sort of, is about 1. So you've got something that's equal to about k. If you can't work that out, that doesn't make sense to you, let me know. Okay, over here, if this is tiny, 1 minus tiny is just almost 1. So this is approximately to kp. Okay, so the growth rate is approximately equal to kp. And we recognize that as the law of natural growth. So it should be exponentially growing. And look at that. For small population sizes, you grow roughly exponentially. Okay? So again, relative growth rate is about k. The growth rate is around kp, so that looks a bit like a line. Good. And over here, you grow roughly exponentially. Okay? Good? Okay, and what's going on there? If the population size is small, you're nowhere near the constraints that would cause any problems. The sky's the limit, or it looks like it is, and so you just grow like crazy. Okay. Good? All right, next piece. I'll post this if you want me to. As the population gets closer to the carrying capacity, relative growth rate gets close to 0, the growth rate gets close to 0, so you change very slowly. Okay? So the population is stabilizing toward the carrying capacity. It's not changing very much over time. Okay? When you hit carrying capacity, relative growth rate and growth rate are 0, you don't move. Okay? So if you start at carrying capacity, you stay at carrying capacity. Okay? So the carrying capacity and 0 are both equilibria or steady states, because once you're there, you stay there. And finally, if you're above carrying capacity, okay, make sure this bit makes sense to you, that if that thing is greater than 1, if this is greater than 1, that this is going to wind up being negative. Okay? And so you're going to wind up down here. Or that guy's going to wind up being negative, so you're going to wind up downstairs over there. Okay? The growth rates are negative, so the population shrinks. If you're above carrying capacity, death rate is higher than birth rate, so you shrink down toward carrying capacity. And that's it. Okay, so those are the regions we talked about. I'll post those slides. If you got any questions, let me know. If you have any questions now, let me know. That's it. Okay? Right. No questions? Okay. Alrighty. Let's do implicit stuff. Hey, it went well this time. Alrighty. Okay, ugly example. Okay, implicit differentiation. Here's an example. Thank you. Find dy by dx. And this example will be y cubed is equal to cos. Keep it down, people. Y cubed is equal to cos x plus y. Okay? I think the ones we did in class are simpler than this, or the one we did in class was simpler than this. Shh, guys. Okay, so implicitly defined, obviously, right? I don't have y equals a function of x. I've got its mess here. The y is buried in here. Okay? So we use implicit differentiation if we want the derivative. All right. Okay, differentiate both sides with respect to x. I'm writing this every time so it's clear. Okay. What have we got? The outside function is cubing. There's the derivative of that, multiplied by the derivative of the inside function, which is y. Don't forget that. Okay? Equals. We've got a composition. The outside function is cos. The derivative of cos is minus sine. Apply that at what it sees. And multiply by the derivative of the inside. Cool? All right. We're using chain rule the whole time here. Derivative of this guy is derivative of this guy plus derivative of this guy. Easy peasy. Derivative of x is 1. Derivative of y with respect to x is derivative of y with respect to x. Now we need to solve for the derivative. Okay, what do? We want to get all these guys on that side. So let's expand. minus sine x plus y. Okay. Minus sine x plus y minus dy dx sine x plus y. Okay, get all the guys with dy dx on one side, get everything else on the other side. 3y squared plus sine x plus y good equals plus sine x plus y. No, minus?
Yeah.
Yeah, minus. Excellent. And then you solve for the derivative. And that's it. Okay, differentiate both sides with respect to x. Don't forget to use chain rule. Get all the dy dx's on one side, everything else on the other side. Factor, divide, solve. And that's it. Okay. One more because it's short.
Could you repeat the steps that you do for those?
Yes, sir. Here?
Yeah.
This is given. Differentiate both sides with respect to x, as indicated. Don't forget to use chain rule. Don't forget that y is a function of x. Expand, and the reason we're expanding is because we want all the dy dx guys on one side and everything else on the other side, and that's what we did here. And I also factored here. And then I divided both sides by this factor to isolate dy dx on one side. I can write that if you want me to write that.
I just wanted to write down
Does it make sense?
like a general
Okay.
rule.
Is that, no? So the general thing is differentiate both sides with respect to x. Don't forget to use chain rule because y is a function of x, and then solve for dy dx. Those are the general steps. Okay? All right. One more. This one's short. Find the derivative. Hey, just to be fun, I'll use y apostrophe this time, or y prime. Okay, here we go. Cos y. Cos y equals e to the x. Okay. Same deal. Differentiate both sides with respect to x. And by the way, if the variables aren't x and y, please don't let that completely derail you. Okay? It's easier than that one. Outside function is cos, its derivative is minus sine. Minus sine y. Derivative of the inside is y prime, or dy dx. Natural exponential function is friendly, it's its own derivative. And we're done. And that's it. Okay? Good? The other example is boring, and too similar to that one. Okay. We did we talked about how we can find the derivatives of inverse functions using this method. And in particular, I did this. Inverse tan. The derivative of inverse tan is 1 over 1 plus x squared, hopefully. Which is weird, by the way. Okay? we did that. If you want, I can do another like that, so I could do that. Is that any use? Who wants me to do that one? That's something. Okay. Who doesn't? Doesn't make you make enemies. That's interesting. Is that a question or is that a vote against?
I have a question. Can you
Awesome.
go back to the last example we did and just explain how you got the minus sign?
Are we here?
No.
No, we're there.
Cos y equals e to the x.
Yeah, cool.
Can you explain
Here?
from the second to the third line?
Yeah, sure, yeah, okay. It's chain rule. Okay, so if you want, this cos y, do we really want to do this? So cos y, okay, so you got an outside function and an inside function. Unless I made a mistake. Yeah, it's an outside function and an inside function. Yeah? The outside function is cos, the inside function is y. Derivative of the outside function, evaluated at the inside function. Cos's derivative is minus sine, evaluated at the inside function, and multiplied by the derivative of the inside function. Does that make sense?
Okay. Yeah.
That's it, it's just chain.
Okay.
Good?
Yeah.
Thank you. Anytime. Thanks for asking. I'll do this one quickly, this arc sine thing. Okay. So it'll look like the arctan thing. It's the same general method. Let's do it. We want this. Inverse sine, if you like. Okay, same deal. Let y equal the function. Then rearrange according to the definition of the inverse. Okay, that's not the whole definition. Don't forget this business. Okay, that was just the definition of arc sine. If you go back, okay, you have to restrict the domain to be able to flip it and make an inverse function. And then differentiate implicitly with respect to x. Okay, derivative of x with respect to x is just 1. We're going to have all that kind of stuff again. Outside function is sine, inside function is y. Derivative of sine is cos, evaluated at what it sees. Multiplied by the derivative of the inside. There you go. And solve. dy dx equals 1 over cos y. Okay. We want the derivative of this, write y equals this, use the definition of the inverse, don't forget that there might be a restricted domain. Take derivatives with respect to x, don't forget chain rule, and then find the derivative, and that's it. Okay, what's the problem? This isn't in terms of x. And if someone asks you for the derivative of arc sine x and you give them something with a y in it, they'll be upset. So let's get it in terms of x, which is sine y. Okay, the identity way is this way. You know that sine squared y plus cos squared y is equal to 1. So you know that cos squared y is 1 minus sine squared y. And now you gotta be careful, okay? Again, sine y is x, so you can just write this. Okay, now, you want cos y. Is cos y square root of this, or minus the square root of this, or could it be both? That's important, okay? And this pain in the butt saves us this time. Notice that if we're there, what does cos look like? Okay, minus pi over 2 is there. plus pi over 2 is there. Okay? And this is y. If we're between those two things, this guy is non-negative. That's a good thing. Okay? Cos is non-negative, so we just get this. Okay? Again, if I didn't know this, and if someone hadn't told me this, or any of that, and they just given you cos squared y equals 1 minus x squared, you can't just write this, okay? It could be plus minus, it could depend, we don't know, okay? But because of this, and because cos is going to be non-negative there, we know that we have to take the sort of upper root, okay? All right, and life's good. We plug that in and we're done. So, conjugate these two and you get this. One over root 1 minus x squared. Okay? And if you ever want to do arc cos, it's just going to be minus that. Okay. And yeah, this thing is differentiable everywhere in the domain except at the ends where you have vertical tangents. Okay? And those will happen at plus minus 1, which is where this doesn't exist. Okay? Again, notice that if you plug x equals plus minus 1 in here, you're dividing by 0, and that's bad. Okay? You're not differentiable at plus minus 1. And that's it. Okay? And our sign looks like this. Sort of. Please. Okay, you got vertical tangents there, so it's not differentiable, and that's why this doesn't work at x equals plus minus 1. Okay? All right. As before, you don't have to do the identity thing. If you want, you can draw some kind of circle. I'm not going to do the whole thing. Base it on this, x equals sine y. Okay, so there's your angle y. X is the sine. Sine is vertical over hypotenuse, or vertical over radius, or opposite over hypotenuse. So it's x, and that's 1. And so Pythagoras tells you that that had better be square root of 1 minus x squared. And so the cos is just that over that. So root 1 minus x squared. Ta-da. Okay, so you can do it that way. If you don't like the identity way. And again, because y can be up here or down here, technically you better be checking both cases. Okay? Okay. Another example like that one, but weirder. If you have a question and I don't see you, let me know. All right, you want the derivative of ln of x. Okay, if you knew that the derivative of ln x was 1 over x, you just use chain rule, right? You just do this. You go, okay, what's the outside function is ln, derivative is reciprocal, apply it at what it sees, and multiply it by the derivative of the inside. Okay, derivative of ln is reciprocal. And that's it, right? But if you didn't know that, if you didn't know the derivative of ln was reciprocal, and keep in mind this is kind of how we figured that out in the first place, what would you do? You'd have to do all this bunk again, so we do this. Alternatively, you write y equals ln x Okay, and then you start rearranging. Okay, you do this kind of stuff. Okay, if y is the ln of this, then e to the y equals this. If e to the y is ln of this, then e to the y equals this. And then you go from there. Differentiate both sides with respect to x. This is almost too hairy to care about. Okay, differentiate both sides with respect to x. Okay, that's just one. The outer function is a natural exponential. Its derivative is itself. So you apply a natural exponential to what it sees, multiply by derivative of what it saw. Okay, again, outer function is natural exponential. Its derivative is itself, evaluated at what it sees, and multiply by the derivative of the inside, which is y, dy dx. Okay, but e to the y was ln x, which is nice. Plug that in. Yeah, that's right. Yeah. Okay. Okay, does that make sense? What did I do? I did all this kind of thing. Okay, I rewrote it in this kind of form that we can handle through implicit differentiation. I took the derivative of both sides with respect to x. I used chain rule twice because there was sort of three functions, do I want to say in series? Yep, in series. So I used the chain rule, and I got this. And then what? I realized that e to the y is just ln x, so I plunked that in there. E to the ln x is just x. And if I solve that, I get that. And that's it. Okay? But if someone just asked you, find this, you'd be crazy to do this, okay? Because you know what the derivative of ln is. Okay. To a related rate thing. Questions? I'm sorry. That's it, right?
There you go, yeah.
Woohoo! Good. And just in time, too. Okay. Excellent. And if you want, I'll lecture you as to where these things are valid and where they're differentiable and what their domains are and all that. If you want me to, ask me and I'll tell you. Because that's the kind of stuff I fuss over. Okay? Okie dokie. If you want another example like that, tell me, I'll give you another. Related rates. Okay, we're going to do the kind of related rates that you classically get as first example. We did the P equals nRT thing, which was benign. Let's do something else. Okay, hang on. I have to write out a problem statement. Okay. If these turn up in your assignments, be funny. Here we go, example. A kite is flying at an altitude or a height of 100, let's go with the noise. Oh, if you're talking to the board, that's a problem, is that what this is? Okay, of 100 meters. Let's change the numbers. 100 meters, can you fly that high? Whatever, 100 meters, 100 feet. Okay. And is moving away horizontally at 8 feet per second. How fast is the angle between, can I see the kite string? Yeah. String and the ground. Shrinking. When 200 feet of string have been let out. Okay. All right, so it's one of those geometric deals. Unlike P equals nRT, no one's giving you an equation. So let's draw a picture. Ground. Your kite is flying. I'm not going to draw the kite. Okay, it's 100 feet up. Okay, we want to know about this angle, so label it. Okay, this thing is moving away horizontally at 8 feet per second. And we want to know about what's going on when 200 feet of string have been let out. Okay. All right, good? Okay. So here's what I'm going to do. Okay, this depends on how you want to do it. I'll tell you how I did it, and it's too much work, but I'll do it anyway. Here's what we'll do. Okay, I'm going to wipe this, I'm going to wipe this. We're going to call this distance x, okay? So that's u, and that's the perpendicular from the kite. We'll call that distance x. How fast it's moving that way is the rate at which this thing is increasing, so it's dx dt. Okay, and we'll call the length of string let out L. Okay, and I'm going to measure time in seconds and all distances in feet. Okay? Okay. Okay. All right. So now what? We need some sort of, okay, so we know what our variables mean, we know what their units are, we have a picture, and now we have to figure out what the heck to do. Okay? So we want this thing. We want the rate of change of theta. And we know about this thing. So we got a decent thing that relates theta and x? Yeah. Someone want to tell me something? How do you relate theta and x? Yeah, go for it. That's good. I heard it, you go ahead too. And then you distribute, you can fight. Yeah, go ahead.
Okay, can you use theta over dx times dx over
D theta over dx, dx over dx. Say that again? D theta over dx?
theta over dx.
Dx dt?
Dx, yeah.
Yeah. Yeah. But to do that, you need those derivatives, right? And to do what you said, and that's good. Yeah, that's both perfect. Okay, so good. So, what do we got? Tan theta makes sense? Okay. Tan theta. Okay. Hola. Okay? You can do that? Okay. And what do you want? You want that thing. So you're gonna have to differentiate with respect to time, as always with the related rates, right? With related rates, you differentiate everything with respect to time. Okay, now how much of a pain in the butt this becomes depends on how you want to do it. Okay, I'll tell you what I did, and it'll be maximum pain. Okay, if you rearrange this like this, I'm just going to make my life a little bit easier by just saying constant here. Okay, although that's what flying horizontally means. Okay, good. So I can rearrange it like that, and then I take derivatives with respect to time everywhere. And then I'll think about what she said. Okay. Constant's derivative is 0. I'm going to flip these guys. Constant's derivative is 0. For the derivative of this, we need product rule. So, derivative of first times the second plus first times the derivative of the second. Okay, we got an outside function and an inside function of time. The outside function is tan, its derivative is secant squared. The inside function is theta, its derivative with respect to time by chain rule. Okay, you could do that. Okay? So what did you do? You made your model, you came up with an equation relating the quantities, you differentiated with respect to time, and that's that. And you did not forget to use chain rule. And now what you could do is you could use all the instantaneous information in here. Okay? So what do we have here? We have that this is dx dt. And that's that. Okay? So we have almost none of this. Okay, so we need theta. We need x. Okay, how do we get x at that instant? We know at that instant that you've got 200 feet there. Okay, so at that instant, we've got 200 feet there. We've got 100 feet there. And this may be a familiar-ish sort of shape. What have we got? You've got 103 there. At that instant. Okay, so you can maybe see that theta is going to be 5 or 6. Okay. We've got everything, haven't we? Yeah, good. Now you can plug in all the instantaneous stuff. Dx by dt was 8. Tan theta. Oh, wow. 1 over root 3. X was 100 root 3. Secant squared That's 1 over cos squared. What's cos? Adjacent over hypotenuse. Root 3 over 2. Root 3 over 2 squared is 3/4. The reciprocal is 4/3. And d theta dt, which is the thing we want. That's it, okay? You got everything, you solve for d theta dt. Move stuff around, and you get d theta dt is equal to minus 1 over 50. And what are the units? The angles are in radians, okay, or nothing, and time was in seconds. So you can write either radians per second or just per second. And that's it, okay? So the angle is shrinking at a rate of 1/50th radian per second. Okay, that was a stupid way of doing it, okay? Now, it was also my way, so there we go. Okay, what you wanted to do was what? Was d theta by dx, dx by dt. Okay, okay, so then how do you write theta then? So you want to write theta as a function like that? It works, you could. Yeah? Okay. Okay, so what do we got? Okay. I think arctan. Yeah, might as well be the same deal. So arctan 100 over x. All log. You take the arctan, you get theta. So you have to differentiate that thing with respect to x. Yeah? And then go through. Yeah? And that works. Now some of this pain can be avoided by not doing it like this. Okay? You could rewrite this. You could just do it this way. You can differentiate both sides of this with respect to t if you wanted to. And that's cool, that works. What does that look like? Okay, differentiate both sides of this with respect to t. You get secant squared theta, d theta dt, equal to 100 times minus x to the minus 2 dx dt. Minus 1 minus 2. There you go. So if you took the derivative of this guy directly with respect to time, you'd get something that looks like that. And then you could work through it that way, if you like that way. Okay? Or, and this is the last thing I'll say, or if you like, you could have written this as cotangent theta equals x over 100. And if you feel like differentiating that, which isn't that bad, that's quite nice. Okay, it's got less gunk than my way. Okay? The lesson here is by rearranging and simplifying, you may be able to make your life better. Okay? And once again, please do not forget that you must only plug in these kinds of instantaneous things once you've taken the derivative. Okay? If you'd been crazy enough to try to plug those things in up here and then take the derivative, you'd just gotten 0, which is bad. Okay? So notice I took the derivatives and then I started plugging in instantaneous values. Okay, that's it. It was previously nonlinear. Any questions about this? Okay. All right. So there's a lot of ways that work. And again, what's the method? Make a model, write an equation, differentiate with respect to time, don't forget to use chain rule, plug in the instantaneous stuff, and solve for the thing you care about. Okay? All right. Let's do another one. I can raise here? Okay.
Ali,
Oh,
can you please repeat what you do after the chain rule?
where?
Like for the steps.
Yeah, sure. All right, what do we do? Model, write an equation, take derivatives with respect to time, which will probably involve chain rule. This morning it only barely involved chain rule. And that's it, you just solve for the derivative. You solve for the derivative. Okay, so either you plug in the instantaneous values, then solve for the derivative, or you solve for the derivative, then plug in the instantaneous values and evaluate. Does that make sense? Somewhat. Yeah. Yeah. But just don't forget, take the derivative first. So the answer to your actual question was plug in and solve. Cool. All right, let's do one more. Related rates again, and again we'll have a triangle. Okay, suppose we have this situation. We have an intersection. We have a police car. We have C for car or possible criminal. Okay. The police car is moving north at 100 kilometers an hour. I'm not claiming this is going to be super realistic. Okay, what else? Is currently 0.3 kilometers south of the intersection. Other car, we'll call it Charlize. Revealing us the first thing that came to mind. Charlize is moving west. The police measures is, she is 0.5 kilometers away. Man, oh man. And this distance is increasing by 35 kilometers an hour. And the question is, how fast is she going?
So wouldn't you be on the other side of that?
Yeah, well, of course, yeah, if you're thinking clearly, yeah. East. Good. Thank you. The luxury of being able to change the question. Okay, police are going this way. This is ridiculous. We're going to make it Charlie, so I sound less pathetic. So Charlie. There we go. All right, hold on. Here we go. So the police are going this way at 100 kilometers an hour. They're 0.3 kilometers south of the intersection. Charlie's going east. Thank you. The police car measures this distance to be ½ kilometer, and the distance is increasing at 35 kilometers an hour. How fast is Charlie going? Okay? Here we go. Let's call this distance x. Let's call this distance y. Let's call this distance z. Okay, so what stuff have we got? The instantaneous information we've got. Y is equal to 0.3. I'm going to measure all distances in kilometers, all times in hours. Y is equal to 0.3. Z is equal to 0.5. What's dz dt? Hmm? Right, so how fast is the distance between the police and Charlie increasing?
35.
35, good. Increasing, so plus. And what's dy dt? Where are the police going? They're going that way. So dy dt is negative, okay? Y is shrinking. They're going this way, so y is shrinking, so there better be a minus sign here. Okay? And the police is moving north at 100 kilometers an hour, so it's minus 100. I'll confess, I was watching the Orville recently. So that would explain my choice of names.
I was returning from a mining expedition in the Matar system, and I encountered a Krull battlecruiser. I managed to outrun it, but it drained my power.
Okay, so what do we got? It's a new, very bad show. Okay, so we're currently 0.3 kilometers south. We're going up at 100 kilometers an hour, hence the 100. We're going up, so this distance is decreasing, hence the minus sign. What else? This distance was 0.5, and it is increasing, according to this thing, so hence the plus sign. And it's increasing at 35 kilometers an hour. Okay? All right. Once you do all this, life's going to be easy. Okay, what can we say about X, Y, and Z? Oh, hello.
Hi. How come that is 0.5 and she's like, I'm just confused about.
Yeah, let's say this. Okay, so the police car from it.
From the police car?
From the police. Yeah.
Okay.
Thank you. Okay, Charlie is that far away and is moving at that speed away. Cool? Thank you. Okay, assume that your questions given to you will be less ambiguous than this. We're good? Okay, how do you relate X, Y, and Z? The obvious way? Yeah, that's right, good. Mr. Greek man, so X squared plus Y squared equals Z squared. Okay? And you may have seen these kinds of questions where you've got a ladder sliding down a wall, which is a classic related rates question. That's going to be a Pythagoras thing too. Okay, x squared plus y squared equals z squared. So there you go. You got your model, you got your variables, you know your units, you know what you know, and what do you not know. You want... How fast is Charlie going? Which is dx dt. How fast is x increasing? Or decreasing? Okay, so what do? We have the equation, differentiate everything with respect to time. Okay, differentiate everything with respect to time. Okay, derivative of this with respect to time. Don't forget to use chain rule. We're going to have 2x dx dt. Okay, the outside function is squaring, its derivative is this, evaluated at x. Derivative of x with respect to time gets multiplied because of chain rule. Similarly for this guy, 2y dy dt. Similarly for this guy, 2z dz dt. Okay, there we go. We got our equation, took derivatives of both sides, didn't forget to use chain rule, and get rid of all these 2's. And there we go, we can solve it. Okay. Alrighty. Oh no, we don't have x, what do? We find it, okay? Okay, so at that instant, x is equal to what? 0.4? By Pythagoras. Okay? Someone told us this was 0.3, then this was 0.5, so this is going to be the square root of 0.5 squared minus 0.3 squared, which is 0.4. Okay? So, some of the stuff you won't be given directly, you have to find it, okay? So that's 0.4. The x dt is the thing we want. What's y? 0.3. What's dy dt? Don't forget the minus sign. Z, 0.5. What's dz dt? Plus 35. And that's it, solve. $118.75. Forget it, let's say 119. 119. Distance units per time units, kilometers per hour. Okay? Same deal, write an equation, differentiate both sides with respect to time. Don't forget to use chain rule. Plug in, solve. Or if you want, solve, then plug in. And then evaluate. That's fine. Okay? This is positive. What does that tell you? It tells you x is increasing. It tells you that we're going that way. Okay, so the answer to the question is Charlie is going east at that speed. Okay? Questions? Okay. I've got a silly related rates one. I'll do that and then we'll stop. Okay, last example. And I'm going to say this exactly how it was given, which is insane. You guys got any dragon questions on any assignments?
What?
Yeah, exactly. Okay.
Wait, I haven't looked at it yet.
What's that?
I haven't looked at it yet.
That's all right. Neither have I, apparently. Here we go. Which one of our dragons is still alive? Well, let's pick one. Okay. You can, I know, right? It sounds like you're just in the mind of a madman. Okay, here we go. So you can. No, they're all alive. It's good.
Oh
my
God! I get it.
Shut up. All right.
I'm sorry. I'm so sorry.
All right, here we go. Cast a spell. This is literally in something today, so this is a copy. You cast a spell to form a spherical shield around yourself. A dragon. One of 3 currently living. Degrades your shield. Decreasing its surface area by What do we got? 8 units meters squared per second. Hmm? How fast is the radius of your shield when the radius is 3 meters?
We have like 4 minutes.
It's funny, isn't it? Watch. This will be easy, okay? You put a spherical shield, this guy's taking away 8 meters squared of its area per second, okay? Or it's degrading it so that the area magically gets reduced by that amount. Here we go. Area, big A, okay, in meters squared. Time, T, in seconds. Radius, R, in meters. Here we go. It's a sphere, okay? Its surface area is given by 4 pi r squared. I hope.
Would it, if it's a sphere, would it be just a circle then?
Hmm?
And it's, you know,
A sphere, yeah, a sphere, and it's in its surface area. So its volume is 4/3 pi r cubed, its area is 4 pi r squared, yeah. Okay, there you go, there's your model, okay? Differentiate both sides with respect to time. The ADT equals 4 pi. Derivative of this, 2r times the RDT. Life's good. Okay, you can plug in. What were you given? Surface area is going down by 8 meters squared per second. Going down. Okay? So this is minus 8. We're talking about when the radius was 3 meters. So this is 3. And that's all there is to it. Okay? Minus 8 is equal to 4 pi times 2 times 3 times dr dt. So dr dt is equal to what? Minus 1 over 3 pi. Okay, meters per second. And that's it, okay? So you knew how fast the area was going down, and from that you determine how fast the radius is diminishing by relating the rates. Thank you, everybody. If you have any questions, come talk to me. Happy Halloween again, and have a good night.